Hello and welcome to Solved Papers channel. My name is Mr. Godfrey. This is a Cambridge IGCSE physics topical questions on radioactivity. These questions are from October-November series exam of 2019. As I indicated to you, topical questions is the best way to prepare for your exams. Topical questions gives you light to the contents of a given topic. Take time to go through your notes, go through your textbook on a given topic, then pick questions that will be set on several years on that given topic. Go through them one by one, take your time, read the questions, understand, and get to know the areas the examiners are fond of testing. In that way, you will be, you'll have upped your game, and as you prepare for the 2021 and beyond IGCSE physics exams. In this video, I will be taking you through each one of these questions of radioactivity that has been set in October-November physics exam series of 2019. And as you know, this way you will be ready for coming exams. So let's get started. And if you have not already subscribed to my channel, please click the subscribe button and hit the bell icon below. This way you'll be notified every time I upload a new video. Question number 1, and as I've indicated to you, these questions are from October-November variant. When you see this indicates to you what question is that. This is question number 37. This question appeared on two variants, paper 1-1 and 2-1 of October-November 2019. So in every question, I give you the paper which the question was appeared and what number that question is. 19 here means 2019. So with that in mind, you can refer and get to know what question this was and what paper it was set. Let's get started with question number 1. Which diagram shows a positive structure of a neutral atom? Right, neutral atom is not charged, is not an ion. When an atom is either having an excess number of electrons by gaining or fewer number of electrons by losing compared to the protons, then we say that is an ion. But this one is a neutral atom. If it's a neutral atom, then the number of protons in the nucleus is equal to the number of electrons. Remember that protons are positively charged, electrons are negatively charged. Therefore, equal positive charge to negative charge will cancel out and the atom will be neutral. So here we are given a key. We are told that this is protons, of course, which we can see inside right here in the nucleus, together with the neutrons. Electrons are found in orbitals. Electrons, you find them in orbitals. Protons and neutrons, these are usually in the nucleus of an atom. And therefore, definitely D is out. You don't find protons in the orbitals. B is out because you don't find electrons in the nucleus. And therefore, likewise also C is out because you don't find electrons in the nucleus, neither do you find neutrons on the energy levels. So the correct answer is A. You can also see that in A we have one proton, all right, and we have one electron in the energy level, and therefore that positive charge of the proton and that one negative charge of the electron cancel out, and that gives us a neutral atom right there. Very well. Number two. And before we go to number two, you can see there's this website here, solvepapers.co.uk. This is the website where you can get all the papers that I'm solving in this. The questions of the papers that I'm solving in this video, and I encourage you to practice working out questions yourself as I guide you. Remember, it's great watching, but practice makes perfect. So you may get this paper and many others from this site, solvepapers.co.uk, and practice, because practice makes key. Can help you with checking the site. This is the soft paper site I'm talking about, solvepapers.co.uk. You'll get all the topical questions in this from IGCSE. Of course, this site is a wonderful site, has got enough resources that will help you as you prepare for your exam. So come to IGCSE, go to physics. There are papers for 2019. So what I'm solving right now is 2019 topicals. Of course, you'll get past papers right there. And we have topicals for all the other years. 2018 topicals are there, 2017 topicals are there, 2016 topicals are there. So I'd like you to get all these topicals and practice. You find that for 2019 November, we have the multiple choice topicals and structured topicals. They're all solved. We also have 2019 June right there. Same multiple choice and structured questions all solved. So you can get all these topical questions. I encourage you to go on the site and get these topical questions. All you need to do is to click this green button here. Click here, get all solved topicals in a zip folder. When you do that, this is where you come in. This is where you'll be brought. This is 2019 November for both physics and IGCSE. These are structured topical questions. We also have multiple questions right there. Also have June, structured for both physics and chemistry. You can get this one for 2018, 2017, and 2016. I'll request you to get help from your parents. You can ask them to get these papers for you. They are basically at a subsided price of £8.99 pounds. Cheap. You get a lot of these papers which will help you in your examination. Therefore, that out of the way, we can proceed to question number 2. Question number 2. Let's go to question number 2 here. Now, question number 2 was from variant 1.1, and this was question number 38 of October-November 2019. So, question number 2, a nuclide of cobalt contains a nuclide. Basically, a nuclide basically means the nucleus of a radioactive atom. Also, a nuclide of cobalt contains 27 protons and 32 neutrons. Which symbol represents this nuclide? All right, this is how we write the nuclide. Of course, cobalt is CO, and therefore, you need to know the correct symbol. You need first to work out the atomic mass of this nuclide. So atomic mass is basically the mass of protons plus, of course, the mass of neutrons. And in this case, we have 27 protons plus 32 neutrons. This will give us 59. So the atomic mass is 59. Atomic mass is usually the upper number of the two. So we have 59 there, and therefore we don't have another 59. 59 is down here and down here. So these are not correct because the lower number of the two gives us the atomic number. So atomic number, which is the number of protons in the atom, is 27. So you can see we have 59 right there, and we have 27 down here, which means the nuclide symbol of cobalt is D. Very good. Number three is gotten from variant 1.1, and this is number 39. You can confirm that. So we are told an isotope, of course, an isotope is isotopes are atoms of the same element with the same proton number but different neutron number. So isotope of radon is radioactive. Okay, so it will undergo decay. It decays by emitting an alpha particle. Of course, alpha particle is an helium ion. Alpha particle is an helium ion that has got an helium ion that has got that does not have electrons, and therefore what happens to the to the nucleus of radon atom during the emission of the alpha particle? Of course, we are told this is radon, and let's say the atomic mass is m and the atomic number is n, and let it undergo decay. Of course, it will decay to element X, and in the process it will emit an alpha particle. We are told that it has emitted the alpha particle, and therefore in this case the atomic mass will decrease by 4, so for m minus 4, and the atomic number will also decrease by 2, so you'll have n minus 2 there, and therefore this basically means n minus 2 is less than n. So this will be an element, a different element with a less number of protons. So what happens to the nucleus of radon atom during the emission of alpha particles? So it becomes the nucleus of a different isotope of radon with fewer neutrons. That is not entirely true, because B said it becomes a different isotope of radon. It is already radon. So since the number of protons has changed, has reduced, then it cannot be radon anymore. So this is a different element other than radon. That makes that option A wrong. B, it becomes the nucleus of a different isotope of radon. Same isotope of radon is wrong. Okay, leave alone more or fewer neutrons. Of course, when it has lost 4 the atomic mass has decreased by 4. It means that both neutrons and protons has decreased. C, it becomes the nucleus of an element with a higher proton number. You can see the proton number here of the resulting daughter nucleus is less than the original protons in the radon atom, and therefore that means this is wrong. It does not have a higher proton number, it has a less number of protons. D, which seems to be the correct answer, it becomes the nucleus of an element with a lower proton number. Okay, with a lower proton number, you can see right there. So the answer is D in that question. Number 4. Number 4 is also from variant 1.1. This is number 40, October, November 2019. Number 4. Why are some radioactive sources stored in boxes made from lead? Okay, of course we know that radioactive sources emit radiation, And we have three types of radiations, if you remember. Types of radiations are three. Type of radiations are three. We have alpha, okay, we have alpha, we have beta, and we have gamma. All right. Alpha is topped by thin paper. Beta is topped by a thin aluminium foil, and gamma is topped by a thin lead or a thick concrete. And therefore, the reason is, why do we store in boxes made of lead? Because I've said that radioactive sources produce these three types of radiation, and therefore they will always be producing those radiations. And let's see which has got a good explanation here. Lead absorbs emissions from the radioactive source. That is correct. Lead will absorb all. None of these three will go past lead, right? Because the most penetrating is gamma, and it is stopped by lead. These others can be stopped by paper or aluminium. So if you have lead boxes, then it means that neither alpha, beta, and gamma will penetrate through, right? What about B? So I think A is correct. I think that's the answer. What about B? Lead decreases the half-life of radioactive source. This is not correct. Half-life is never affected by an external factor, and that is not the reason of storing in lead boxes. Lead increases half-life. That is not correct. Of course, you remember half-life is the time taken for the original number of nuclides to decrease by half. D, lead repels emissions from the radioactive source. Likewise, that is not correct. So lead absorbs, does not repel, absorbs the emission from the radioactive source such that they don't penetrate the box, and that means that people in the room where the box is are safe from this radioactive radiation. You know, these radioactive radiations are ionizing, and therefore they can easily mess you up if you get exposed unnecessarily too long with the radioactive sources. Okay, number 5. Let's go to number 5. Right there. Of course, number 5. This was a question in two papers, variant 1-2 and 2-2, and it was in both questions. It was question number 37. Okay, so the diagram shows the simple atomic structure for two neutral. That's key. Two neutral atoms, X and Y, of different elements. If they have different elements, they should have different number of protons. Which row is correct? All right, atom with more electrons, okay, and atom with more positively charged nucleus. The reason for positively charged nucleus is protons. Protons are the particles that are positively charged. So our task here is to find how many electrons do we have in X, and how many protons do we have in the same, right? Since we are told the atoms are neutral, they should be having the same number of electrons. So once we identify the electrons, like here we have 3 electrons. X has got 3 electrons, and therefore it means it has got 3 protons because it is a neutral atom. What about Y? Y has got 1, 2, 3, 4 electrons, and therefore it should also have 4 protons for it to be neutral. So let's go here. Which row is correct? A, atoms with more electrons is not X. The atoms with more electrons is Y, because Y has got 4 electrons compared to 3 electrons of X. So both A and B are wrong. So we're talking about C and D. So the answer can be either C or D. Let's go to atoms with a more positively charged nucleus. And of course, positivity is due to protons, we have said. And therefore, Y has got 4 protons, excuse me, as compared to 3 protons in X. Therefore means that Y has got a more positively charged nucleus, meaning the answer is D right there. Yeah, let's continue to number 6. Number 6 is right there. Number 6 was set from variant 1, 2, and this was number 38. So a nuclide of chlorine as the simple this. It has got atomic mass of 35, atomic number of 17. What is the nucleon number of this nuclide of chlorine? Nucleons, these are particles found inside the nucleus. And we have 2 particles inside the nucleus. We have protons and we have neutrons, right? And we know that atomic mass, is usually the sum of protons plus neutrons, and therefore atomic mass, this gives us what we call the nucleon number. So for a nucleon number, you look at the atomic mass, and the atomic mass in this case is 35. So C is correct. Number 7. Right there. Of course, number 7 is from variant 1, 2, and this was number 39. Of course, this is October-November series of 2019. Which type of radiation can be stopped by a sheet of paper? Of course, we say that alpha is stopped by paper. Beta, we have 3 types of radiations, is stopped by thin aluminium, and gamma is stopped by lead. So the question is a sheet of paper. So that basically means the answer is A. Okay, number 8. Number 8, of course, it's from the same variant, 1, 2. Now this is number 40. Why are some radioactive sources stored in boxes made from lead? We have looked at this question up there. I think it was question 5 or 4. Can confirm. So the answer we found it is A. You find these questions repeated from one variant to the other, so it's not a big surprise. Question number 9 was set from 2 variants, 1, 3 and 2, 3, and this was in 1, 3 it was question number 37, and in 2, 3 it was question number 38. So the diagram represents a neutral atom, equal protons to equal electrons. Which row identifies each type of particle in the diagram? Of course, you can see inside the nucleus we have 2 types of particles, the ones which are not shaded and the ones which are shaded black. In the orbitals we have electrons. These are electrons, okay? And inside the nucleus we have protons and neutrons. So which are the neutrons and which are the protons inside? To know that, you always remember that in a neutral atom, protons, the number of protons is equals to the number of electrons. And how many electrons do we have here? We have 2 electrons, and therefore that means that we have 2 protons. That is what is going to guide you to know inside the nucleus which are the protons and which are the electrons. So we can see we have only 2 shaded black shaded circles, so those are the protons. So this is correct, proton. So then it means that the unshaded circles, those are neutrons, Therefore, this is a neutron, correct? And then the electrons are the ones in the energy level, so it means the answer here is A. Number 10. Number 10 is from variant 1.13, variant 1.3, and this was question number 38. An ion nuclide is represented by the symbol shown here: atomic mass 56, atomic number 26. Of course, Fe is the symbol for element ion. Which statements about the nucleus of this nucleus are correct? Now, statement 1. The nucleus contains 56 neutrons. Let's see. Of course, we know that 26 is the number of protons, and 56 is protons plus neutrons. Therefore, if protons are 26, then how many are neutrons? So therefore, neutrons are 56 minus 26, and therefore neutrons are 30. And statement 1 says that neutrons are 56. Therefore, statement 1 is not correct. Statement 2, the nucleon number is 30. You have said that the nucleon number is equal to the number of protons plus the number of neutrons in the nucleus. So nucleon number is equals to atomic mass, which is equals to protons plus neutrons, right? So the atomic mass is 56, and therefore the nuclear number is 56, not 30. So that is not correct. The proton number is 26. We have already said that the number of protons is 26, and therefore statement 3 is correct, which means that D is correct. Before continue to number 11, I'd like to welcome you to join me at my online classes. I have online classes at this site we call SP Academy. We have this site we call spacademy.co.uk. Here I do online tuitions. And therefore I welcome you to join me at SP Academy. And this is the site I'm talking about here. This is the SP Academy. Basically, SP is short of Soft Papers Academy. We have an academy where teachers meet their students online and do live or real-time classes, just like the way you do in Zoom. We usually use a different software we call BBB, which is very effective. So I'd like you to join me in this my online classes. I'd like you to log into this site and go to here, student guides. If you are a tutor, you can just look at the tutor guide. Click here for a step-by-step guide for students' dashboard functionalities. If you join up and sign up, you'll be have your own dashboard where you can manage things for yourself. I will also ask you to take time and watch this video here to get familiar with our online live classes. Basically, we have ICT, mathematics, physics, biology, chem. You can contact me for physics. The other teachers handle the other subjects. You can contact them as you need. And of course, physics, I teach all the way from checkpoint to A level, including what I'm handling right now here, physics IG. And we keep adding these subjects as request comes through to us. And of course, we've got very positive reviews here. If you can look at them, you have students from all over the world. We teach students from Dubai, Abu Dhabi, London, US, and many other places on the globe. So I'll encourage you to consider registering. Come here to register. Of course, I'll need you to register and create your own account, and you'll get an email which you can activate your account. Then you can come here and join, sign in. You can find a tutor. By going here. You'll find the number of tutors that are available, and you can also come here and do some other more walkthrough in our site. So I encourage you, and I guarantee you will discover a great opportunity of getting outstanding grades, which I know you are after, which will see you for the next level. So hopefully you can register and I meet you in my online classes. Then we can take this one to the next level. Thank you. Let's look at number 11 now. Number 11. Okay. Number 11 is right here. Number 11 is from variant 1.3. This was number 39. Three types of radiations, we know them, alpha, beta, and gamma, can cause ionization, right? Which row identifies the least and the most ionizing of these? Of course, the least ionizing is gamma. Gamma is the least, and the most ionizing is beta. Is alpha. So look for that. So the least ionizing is gamma. C and D are correct, and the most ionizing is beta. Is alpha. So D is the answer for that question. Number 12. Number 12 right here. From this is question that appeared in two variants, 1.3 and 2.3. In variant 1.3 it was number 40, and in variant 2.3 it was number 38. Why are some radioactives stored in, right? We have met this one earlier on. So this is a question that has been set now in 4 variants out of 6 variants. So doing topical questions exposes you to the kind of questions that are repeated in various variants, and this opens you up to the fact that you can get these questions in most of these variants, and that tells you where do examiners focus on mostly. So number 13, I think we are done with number 12. Got number 13. Number 13 here. Number 13 is an extended question. It was set in variant 2.1, and this was question number 38. The scattering of particles by a thin gold foil provided scientists with evidence for the nuclear atom. Okay, this was done by Rutherford with assistance of his 2 undergraduates, Giga and Marsden. Which particles were scattered by the by the gold nuclei in the thin foil? Which particles were scattered by the gold nuclei? Nuclei is plural of nucleus. In the thin foil. Of course, when they did this kind of an experiment, Giga and Marsden were using alpha particles. So the answer to this question was alpha particles. Now, they were scattered. The alpha particles are positively charged helium ions, and when they came near the atom, then the nucleus of an atom, they were repelled. This scattering here is because of repelling. Okay, they were repelled by the positive charge in the nucleus, and that positive charge turned out to be protons. Before this experiment, this was not known. So protons are positively charged, and that is this experiment is what meant to discover the nucleus of an atom. Before then, there were other models of atoms which were not correct. So number 13, the answer is A. Right, number 14. Number 14 was it's found in variant 2.1, and this is number 39. And number 14, the diagram shows a beta particle. Beta particle is basically a fast moving electron. That is what we call a beta particle, and electron is negatively charged. Now, being directed between the poles of a magnet, right? In which direction will the particle be deflected? Now, to answer that, you need to use Fleming's left-hand rule. Use Fleming's left-hand rule. Okay. Fleming's left-hand rule. I think it's right-hand rule, if I'm not wrong. Right-hand rule. And remember current is the flow of in a circuit. Current flows from the positive terminal to the negative terminal of the battery. All right. So if you have a circuit here, so the convectional flow of current in this way. So since these are negative particles, we know that electrons flow in the other direction. These are electron flow. So electrons flow in the opposite direction of current, and therefore, if the negatively charged beta particles are flowing this direction, then current is flowing in the opposite direction. This is current, right? So you use your right-hand rule and identify Fleming's right-hand rule and identify the direction in which it will be deflected. And when you do that, then your thumb will be pointing out of page. Current is second finger. Your second finger will point in the direction of current. Then I think this is left-hand rule. I'm mixing these two. This is left-hand rule. Okay. So first finger is the direction of field, which is downwards, right? First finger. This is first finger, and this is second finger. Will point in those directions. Therefore, you'll find that the direction of deflection of the alpha particles inside the magnetic field between the north and the south poles of this magnet will be out of page. So the answer is B right there. Number 15. Number 15 is from variant 2.1, and this is number 40. Why are some radioactive, this is repeated many times. I don't know why we just did not do it only once. Okay, let's go to number 16. Number 16 is right here. Plutonium 238. This is usually the atomic mass. When it's written like this, you understand that it's atomic mass. Plutonium 238 decays by the emission of alpha particle. The equation which equation represents the decay of plutonium nucleus? So alpha particle is usually this, so you look for that. So A is not correct. That is not the correct symbol of alpha particle. So and C is not correct because the atomic mass is 4, atomic number is 2, so that is not correct. So the answer is between B and C. And therefore, when it decays by emitting alpha particle, then the atomic number decreases by 4. Therefore, the atomic mass, so the atomic mass now should be 234. And the atomic number, which is 94, decreases by 2, and this should be 92. So that's what you'd be looking for, 234 and 92. So 234 is here, and 92 is here. Consider this is 242. So the right answer is B. Number 17. Number 17 there. A radioactive isotope. Of course, 17 is from variant 22, and this was number 39. A radioactive isotope has a half-life of 8 days. As I said, half-life is the time taken for the nuclei to reduce by half. If there are 1,000, the time it takes for the nucleus to reduce by 500. A detector close to a sample of this isotope gives a count rate of 200 counts per minute. Without the source, the background count is 20 counts per minute. What is the count rate due to the source after 8 days? Okay, after 8 days. We are told half-life is 8 days. So after 8 days, that would be just one half-life. And to do that, we've got to get the count rate to decrease by half, or to half. And we know that we are given the background radiation here. So this count rate here contains this background radiation. So the initial count rate should be minus the background radiation, which gives us 180 counts. So 8 days is only one half-life. Okay, so it will decrease from 180 to 90. Okay, this is only one half-life. When you half from 180 divide by 2, you get 90. So what is the count rate due to the source? Due to the source, not plus the background radiation. So the count rate due to the source is 90 after 8 days. If the question was, what is the reading of the meter, then you need, after you get 90, you need to add 20. So it will be 110. But this time is due to the source after 8 days. So you do not add the background radiation again. So it's basically 90. Number 18. Number 18 was set variant 22, and this was number 40. Why are some this question is asked many times over. Next time I will do good. So the answer is that. Number 19. Number 19 was set on variant 23, and this was number 39. Okay, so a thin metal foil is placed in a vacuum. Thin metal foil. Alpha particles are fired at the foil, and most go through straight. A very small proportion of the alpha particles are deflected through large angles. What does this provide evidence for? Of course, deflection and firing of alpha particles. Always remember the alpha particle scattering experiment of Giga and Marsden under supervision of Professor Rutherford, and therefore this is where the nucleus of an atom was discovered. Therefore, without question, you just look at where there is nucleus. Alpha particles are very small, we know that, but that was not what the evidence this experiment can give. There are negative electrons in each atom. There is no such evidence, because provide evidence for. There is a tiny nucleus in each atom. Alpha particles are positively charged. Okay, and if they are deflected, is due to another positive charge, which means the nucleus should be positively charged. There are neutrons in each. This is not correct, so the answer is C. Question number 20. Okay, number 20. Sorry. Number 20 was from variant 22.3. This was number 40 in that variant. The background count rate measured by radiation counter is 40 per minute. Okay, with the counter close to a radioactive source, the count reading is 96 counts per minute. The half-life of the source is 20 minutes. What is the counter reading? 1 hour later. Okay, 1 hour is 60 minutes. When you divide by 20 minutes, you get 3. So this is going to be 3 half-life. So 3 half-lives. That's what you'll be considering. Now, we're given the background radiation. So to find the count rates for the radioactive source, we have to take away the background radiation, because background radiation is usually constant, does not vary with time, does not decrease with time. So then, of course, we have 960 there. We take away 40, which is the background radiation, we get 920. So we find after 3 half-lives, what would have the count rate decreased to? So 920 for the first half-life. It will have decreased to half of this, which is 460. The second half-life, it will decrease to 230. Don't forget we are doing 3 half-lives. Then the third half-life, it will decrease to 115. Now we want the counter reading. This is the count rate of the radioactive source without considering the background radiation. But the background radiation is there, and therefore the counter is reading both this radiation from the radioactive source and the background radiation. And therefore, now we take 115 plus the background radiation, which is 40, and this will give us 155. 155 counts per minute will be what the counter reading will show. Right, so 155 is right there. So that is the count the meter will read, the number of counts plus the background radiation. And therefore, that's the end of this radioactivity paper. As I've indicated, look out in softpapers.co.uk and get more topical questions and practice on those, and I guarantee you will be set up for good performance in your exams. All the best. See you in my next video. Bye.